As a classic demonstration of parametric resonance, consider the humble pendulum. By vertically driving the system at 2 omega naught, the pendulum exhibits instability. That is, the swinging arm's amplitude increases exponentially. But what happens if you rotate the system 180 degrees? Does the instability of the normal pendulum lead to stabilization of the inverted pendulum? Moreover, under what conditions is the inverted pendulum stable? To begin, it is convenient to analyze the system from a non-inertial reference frame. A consequence of this choice of reference frame is the introduction of a pseudoforce due to the acceleration of the frame. This pseudoforce, the force of inertia, is given by negative y double prime of t, where y of t is the time-dependent motion of the vertical coordinate of the pendulum. Let y of t be a sinusoidal forcing function. Y of t equals a cosine omega t. Therefore, the pseudoforce is given by f of t equals negative a omega squared cosine omega t. We define stability to be when the average value of the torque due to the pseudoforce can be greater than the average value of the torque due to gravity. We define the torque due to the pseudoforce to be negative 1/2 m a squared omega squared cosine c sine c, and the torque due to gravity is negative mgl sine c, where c is the instantaneous value of the angle of deflection. Since we are only interested whether or not the torque due to the pseudoforce can exceed the torque due to gravity, we make the following inequality. Canceling out terms yields a omega squared is greater than 2gl. Using the fact that omega naught equals root g over l, we find the following. If a over l times omega over omega naught is greater than root 2, the system is stable. We can ignore the cosine c term because we are only interested if this system can exceed a certain value, not whether or not it always does. In the top right-hand corner, you can see a simulation where the parameters are such that a over l times omega over omega naught is slightly less than root 2. Therefore, we see an instability in the pendulum. We could also find this lower stability condition using the Matthew equation, which is the second derivative of phi in respect to time plus negative the natural frequency of the pendulum squared plus the amplitude times the driving frequency squared times cosine omega t over L times phi is equal to 0. However, this equation uses the small angle approximation and therefore is not valid for angles that are large. Therefore, our analysis using the pseudo-torque method and the torque due to gravity is more applicable to a wider range of problems, such that the initial angle is much greater than the small angle approximation would allow. As a simpler way of explaining the stability of the pendulum, we will look at the extrema of the motion, where the pendulum makes its greatest angle in respect to the vertical. At these points, we know the torque due to the accelerating reference frame has to be the greatest and point such that the force due to the torque directs the motion of the pendulum towards its equilibrium position in the center. This is true for both sides of the extrema. Also, we know that at the vertical, when the pendulum is completely vertical, there should be no net torque. This can be seen in the V-Python simulation, where at the extrema, the torque is the greatest at these points and the torque is 0 at the vertical. But what happens if the torque is too great at the extrema? Will the system destabilize again? Is there an upper bound to stabilization of the inverted pendulum? To see if an upper bound of stability exists, we return to the equation of motion. If we make the approximation sine of phi is close to phi, we return to the Matthew equation with the relevant solution being a over L equals the square root of 117 plus 232 times omega naught over omega squared plus 80 times omega naught over omega minus 9 minus 4 omega naught over omega squared all over 4. We return to the Matthew equation because we see that in the spectra of motion for the inverted pendulum, there are two primary wave packets, one at half the natural frequency, or the first harmonic, and the second one being at the third harmonic. This is very much like the normal pendulum. Therefore, to address the instability of the upper position, we return to addressing the situation of the normal pendulum and address instability of the lower position, as analogous to the upper position. Using computational models, we can verify that this method works. Now that we have found both an upper and lower boundary for stability, we can plot these curves together and look at the zones of stability for the inverted pendulum. It is interesting to see that as the driving ratio of omega over omega naught decreases, the zone of stability also decreases. This means that as the driving frequency becomes closer and closer to the natural frequency of the pendulum, the amplitude over the length of the pendulum has to increase, and it becomes increasingly hard to satisfy these requirements for having a stable system. Since we use the small angle approximation to find the upper boundary, we can compare a computational model to the analytical solution. We find that for large driving frequencies in respect to the natural frequency, the results are consistent. However, for small driving frequencies in respect to the natural frequency, we see slight deviations from the curve. So much so that at anything below 2 omega naught, the system is unstable, meaning that no matter what combination of amplitude and length you try, the system will not stabilize. This result contradicts the analytical solution, which says that there should be a stable combination within this zone. This could mean that the sine phi term is contributing a lot more to the motion of the pendulum than previously expected, causing this irregularity to show up in the computational model. This is a limitation of using the small angle approximation for pendulums.